we're going to answer the do not questions just right up on the document camera. So consider this reaction. So this is the exact same thing that was just on the board. I just put it on a piece of paper to make it easier for us. So before we worry about the 4 changes that we're going to make, I want to start by looking at delta H. So remember that delta H tells us if it's endo or exothermic. So if delta H is negative 563 kilojoules, when delta H is negative, right, less than 0, that means that heat is released, which means that it's exothermic. The reason that this is important is because if we talk about changing the temperature, we need to know what type of process this is. If it's exothermic and heat is released, I can think about adding heat as a product. When heat is released, we can think about heat as a product, and then we can kind of go from there. So the first change that we're making, so remember this is like being at equilibrium, right? Our ratio is balanced. Then we make a change, right? We're making a change to a system that's already at equilibrium. So this says we remove CO. So here is CO on the reactant side. If we're removing CO, right, we're taking carbon monoxide away. Well, now we're no longer at equilibrium, right? Now we don't have enough reactants. We just took some away. So the reaction is going to shift in a way. We don't have enough reactants. It's going to shift so that we make more reactants. So if we're talking about shifting to make more reactants, we can say shifts left. Right? Left means that the arrow is pointing from right to left. That means products are going to be creating more reactants. Or you can also say shifts toward reactants. That means that reactants are produced. Number 2, for adding H2 gas. So now we're back to equilibrium. We're back to equilibrium. Now we're adding H2 gas. So now, I'm going to try to do it in a different color. So we're adding more H2. So now we're not at equilibrium because now we've added more reactant. So now we have too much reactant. So if we have too much reactant, the reaction needs to shift so that we can use up that excess reactant. So if we need to use up the excess reactant, we're going to use up reactants. We're going to make more products. So for number 2, we'll say shifts right. Or we can say shifts toward products. Now, raising the temperature. So this is why adding heat was important. I'm going to try to use different colors for every scenario. So raising the temperature means you're adding heat. When you raise the temperature of something, you're adding heat. So I wrote plus heat over here. If I am adding heat, that's like adding a product. So if you think about being at equilibrium, now we've added more product. Now we have too much product compared to reactant. So if we now have too much product, we need to use up the product, make more reactant. So for this one, we would say shifts left or shifts toward reactants. In all of these, we're shifting in a way that's undoing or trying as much as possible to undo the change that we made. And then finally, number 4, increasing the volume of the container. Changing the volume is having you think about pressure. So we have a container, right, which has a certain pressure. We increase the volume. What's going to happen to the pressure in that container? What's going to happen to the number of collisions if it gets bigger? They're going to decrease, right? There's less collisions. So just to write what's happening here, if we increase volume, we're decreasing pressure. That's the change. That's this change that we're making to equilibrium. So by increasing the volume, we're decreasing the pressure. But to remain at equilibrium, it needs a certain pressure. And so what needs to happen is it needs to shift to make more pressure. All right, this needs to shift in some way to make more pressure. And the way that it's going to make more pressure is by shifting to the side of the reaction that has more moles of gas. Because the more moles of gas that you have, the more collisions that there are. So if you look at the balanced equation, we have 3 total moles of gas on the left, 1 mole of gas on the right. Just look at the coefficients. So if we want to make more pressure, we need to shift toward the reactants. So we'll say shifts left toward reactants. All right, so we have left, right, left, left. Yeah, so you're just adding when you're looking, and actually this will actually probably help for mastering as well. When you're looking at counting the number of moles of gas, because that's what you need for the Kp and Kc conversion. When you're looking at number of moles of gas, you're just looking at the coefficients. So like here, oh, you can't, well, kind of. All right, there's 1 CO and 2 H2. So that's 3 moles of gas on the left. The coefficient in front of CH3OH is a 1, right? If there's nothing there, it's a 1. So there's 3 moles on the reactant side, there's 1 mole on the product side. So you're just looking at coefficients in that case. Any other questions on the do now? Yeah.
I have a bunch of questions.
Yeah.
Okay, so you added heat to the products.
Yes.
Because it's exothermic. If it were endothermic, you would add it to the reactant.
Yes.
It's
Because
always like that.
yes, because if it's endothermic, heat needs to go into the system.
Right.
And so if it needs to go into the system, it acts as a reactant. So always, if it's exothermic, heat is a product. If it's endothermic, heat is a reactant.
Okay.
Yep.
And then when you go to determine what side it shifts, I always get them switched up. Is it like what you're needing, kind of? Like for number 1, you're removing the CO. You need to make more reactants because you just took a reactant out, so you need more stuff on the left.
Yes.
Okay.
Yeah, so when we talk about which way it shifts, thinking about shifting left means you're making more of what is on the left side of this double arrow. Shifting right means you're making more of what's on the right. So if you're taking reactant away, you no longer have enough reactant, you have to make more. And if you're making more CO, you're also making more H2 because you can't just make one reactant, right? You're going to be making all of the reactants.
Wait, but why are we choosing the side with the bigger coefficient, like value?
So for number 4, because we are increasing the volume of the container, that's decreasing the pressure. So changing the volume affects the pressure. So equilibrium exists at a certain pressure. Well, by changing the volume, we've brought the pressure down. So instead of the pressure being up here where it needs to be, now it's down here. And so to get back to equilibrium, we need to bring pressure back up. And so to bring pressure back up, we're going to make either more reactants or more products, but we want to make more gas. And so since the reactant side has 3 moles of gas, as we make more reactant, we have more and more collisions, so pressure will be able to come up more quickly.
So
yep.
You can't, I don't know if it's in, but if you did increase the products, it would take a lot longer.
Yes.
So like that's not
right.
Okay.
Right. Yep.
Technically, we wouldn't be wrong if we said products. You could just write it would take longer.
Or, I mean, and I guess you have to hope that if you shift to the products, you don't run out of reactants.
I'll just put the right.
Yeah. Any other questions?
Wait, so what is it like no effect? Oh, is that like the change in K?
That's, so yeah, the only thing on here that changes K is temperature.
Right.
The other thing that would be no effect for shifting is a catalyst. so a catalyst won't affect it. Or if you try to add like a noble gas, like if you try to add neon, right? Noble gases are unreactive. And if you also notice in here, there's no neon in here as well. So adding a noble gas doesn't affect anything either. So yesterday, the no shift was adding a noble gas or adding a catalyst. Yeah. And then the other one when we looked at, there were a lot that were no effect. That was when we looked at K.
Oh.
Yeah. Any other questions? No. All right. So that's it for the do now. Kind of just thinking about shifting left, shifting right. I did put up the examples from yesterday. So if you need to go back for some reason, or you just want to review, all right, the examples are up. The next thing that I want to look at, so I'm kind of going back and forth between the slides and, let's see. No.
Did we make anything last night?
No.
Okay.
I've been doing this on the wrong page.
So we're going to look at the slides for just a second so that I can kind of talk about the lab for today. So today and tomorrow, we're going to do kind of a review lab. I can't find silver nitrate in order to try to do it in person. And actually, the way that I was thinking about doing this with pictures, a professor at a college already did, and someone sent it to me. So I was like, perfect, less like pictures I have to take in the lab. But this is going to be a lot of reviewing for Le Chatelier's principle, writing K expressions, looking at Q versus K. And so we're going to spend today and tomorrow going through this. The lab handout, so for you guys that are in class today, the lab handout is in the top tray. So if you want to grab the lab handout in the top tray, you can grab that. You guys that are on Google Meet, if you did not grab it yesterday in class or you're online and you didn't get the link, it is posted to the assignment in Google Classroom that just went up this morning. So there's a Google Doc or there's a PDF if you want to print it out. So I pushed out an assignment in Google Classroom this morning that actually has the handout and then also has the link. So this link right here, if you don't want to type it when the time comes in the lab, the link is in the assignment in Google Classroom. So you can go in there, you can click on it. I'll show you what it looks like. We're gonna actually go through the pre-lab together. So like I'll have you working on a question, we'll go over it, do a question, go over it kind of like that. And then you'll be able to start looking at collecting data. Now, just one quick thing, just give the simulation time to load. When you click on a button, if the pictures don't pop up right away, just give it a second. But then we'll go through the questions in the lab handout. So between today and tomorrow, we should be good. We're even going to do post-lab questions together as well. So we'll make sure that any questions get answered as we go through this lab. But I just wanted to be able to kind of review, even if it is just looking at pictures. The only thing that, the only difference between like doing the pictures like this and doing it in the lab is that instead of clicking on a button that says add KCl, you literally just went KCl and looked at it. Like that's all the lab is. It's just adding something to a test tube. So we're not missing out a whole lot. And so what we're going to do is we're going to go ahead and look at some of the pre-lab questions. So in the lab handout, we're just going to start on the first page. So you guys on, that's not what I want. Okay. No, you're not doing this lab in your lab notebook. So it's actually just going to go right on here. It'd be way more writing to do it in your lab notebook. So you can actually just do it right on either the Google Doc or the PDF. I mean, I guess if you want to do it in your lab notebook, you can, but you don't have to.
What's next?
More equilibrium,
Really?
and then more equilibrium.
What did you just say? What's next?
Oh.
Acids and bases.
No.
Yay!
More? More equilibrium?
Equilibrium is 3 chapters.
Oh my
Bro,
god.
what? Oh. So
Yeah.
do we have a huge unit test on all 3?
No.
Oh.
It's like each one is individual.
Oh, so like thermodynamics was like chapter blah 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 blah.
Yeah.
But like,
What did
Yeah.
you say? What are you saying?
I know what you're saying. Yeah.
What? Yeah.
Okay. So for the pre-lab, again, so Emily asked a question, and I didn't even think about it. This is not going in your lab notebook. Like this is actually just, you're gonna answer right on here. Now, if you want to do it in your lab notebook, you can, but then you're gonna be like writing more tables and stuff. So you can actually just do it right on this sheet. Like I gave you space, I spaced everything out so you can work through it. So for pre-lab questions, we're gonna just go through. There are actually, I don't know how many, 7 pre-lab questions. But we'll go through, we'll answer some. I'll have you look and see if you can answer. We'll go through, we'll make sure you have all of them answered. So for number 1, French chemist Le Chatelier put forward this principle: fill in the blanks to complete the following sentence. So if a system at blank is disturbed, so first, what does the system have to be at when it's disturbed? Equilibrium.
I mean,
You're okay.
All right, so if a system at equilibrium is disturbed by a change in, so it's blank, pressure, and concentration. So we looked at pressure, concentration, temperature. Right. So if a system at equilibrium is disturbed by a change in temperature, pressure, or concentration, the system will shift its equilibrium position to counteract the effect of the disturbance. So there's number 1, just definition of Le Chatelier. So then for questions 2 and 3, it says consider this system represented by the chemical reaction below. Number 2, which of the following happens when additional H2 is added to the reaction mixture that is at equilibrium? So now it's at equilibrium and we're adding H2. Now, if you just do a quick glance at these multiple choice options, notice that it talks about Q versus K. So let's think about it in terms of Q versus K. I'm going to write my Q expression. I'm just going to use QC. It doesn't really matter. It doesn't specify. I'm going to write my QC expression. Products over reactants. H2 times I2 over HI squared. So if additional H2 is added, I am increasing the amount of H2. I'm increasing the amount in a numerator. Well, remember, when this is at equilibrium, so before this was at equilibrium, which meant Q equaled K. Well, if we're adding more H2, now we're not at equilibrium anymore. We're adding more to the top. We're increasing the value of Q. So by adding more H2, you're adding more to the products. That's increasing your value of Q because Q is products over reactants. So once you answer that, here's what I recommend. Look at your answer choices that you can now eliminate. All I did was glance and notice that it was Q versus K. I didn't read all of them. I just saw Q and K. I know that Q is greater than K. I'm eliminating A and B. Now, let's think about what it means for Q to be greater than K. Well, here's Q. Here's K. Remember that the arrow points in the direction of what we need to make more of. All right, points toward the reactants. We need to make more reactants. You can also think about it using Le Chatelier's principle as well. All right, if I think about it, adding more H2 means too many products, not enough reactant. So it needs to shift in a way to get back to equilibrium. So too many products, not enough reactants means we need to make more reactants. So we want C. Q is greater than K, the reaction shifts toward the reactants. D is not a correct statement because if Q is greater than K, the reaction will always go from products to reactants, right? We need to bring K or Q back down. Now number 3, so again, this is still based on this equation up above. Which of the following happens when I2 is removed from the mixture? So now, if we look at Q up here, if I remove some I2, well, now I'm taking products away. So now instead of Q being equal to K, now I don't have enough in my numerator. So I have a small number divided by a big number. That change just made Q less than K. So if I think about it again, here's Q, here's K. So I have to go from reactants to products. By removing I2, we don't have enough products. Notice I'm still just answering the question over on the side. I haven't even read any of the multiple choice answers yet. Try to answer the question first and then see which multiple choice response matches how you answered the question. So not enough products. So we need to make more products. So let's look and see. First, I know that Q is less than K. So I can eliminate C and D. Then we read the rest. Q is less than K in both of these. Reaction shifts toward reactants or products. Well, we said there's not enough products, so it's going to shift to the product side. That's B. So because we're thinking about Q versus K, at equilibrium, Q equals K. Once you start making changes, you're affecting what's in the numerator or what's in the denominator. So looking at number 4, now we're looking at a different problem. At 1000 Kelvin, SO2 and O2 can react to form SO3 as represented by the equation above. All right, if you just grabbed one of the handouts from the top tray, or if you grabbed one yesterday, for those of you that are in green, we need a double arrow in here. There should be a double arrow between O2 and SO3. I was working through this yesterday and I was like, where's the arrow? So for those of you that are looking at the Google Doc or the PDF, I updated this yesterday. So it should read 2SO2 plus O2 is at equilibrium with 2SO3. Now I want you to answer part A. You should be able to do part A. Write the expression for the equilibrium constant Kp for the forward reaction. When it says for the forward reaction, that just means SO2 and O2 are your reactants, SO3 are your products. So write the Kp expression. All right, so you're writing the Kp expression. Bless you.
What?
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 Yeah. I know that you're bad.
What? Bless you.
Is there all of has these?
That's not how you're saying this.
I tried.
My father-in-law. No, my Anisha's dad sneezes, and it is, you can hear him from a mile away.
Yeah, I tried.
It's the most obnoxious, high-pitched sneeze. And now Anish thinks it's funny, so then he starts doing it. I'm like,
Not you, not you.
I do not. No, thank you. That's not what I signed up for.
My brother and my dad do that too. They like scream.
Like, shut up. Like, it doesn't need to be that loud. Stop.
Oh, like mine. I think I tried to hold it in.
It just sounds like. Wait. I don't know what it sounded like.
It sounded like you did that.
All right, so for your KP, P is pressure, products over reactants. Don't forget exponents. Pressure of SO3 squared over pressure of SO2 squared times pressure of O2. Right? Products over reactants. Writing the K expression just means products over reactants. These are all gases, so you can include all of them. So now part B, an equilibrium mixture. I'm going to underline that because that's important. An equilibrium mixture is established at 1000 Kelvin that contains the following partial pressure values. Calculate the value of the equilibrium constant. Well, remember, to solve for the equilibrium constant, you need equilibrium amounts. That's why this was so important that it says an equilibrium mixture. This is already at equilibrium. So since this is at equilibrium, we can plug right in. So since this is already at equilibrium, we can just plug right into Kp. So take these pressures and your Kp expression and see what you get for Kp. So again, the reason that we can plug these partial pressures directly in is because it says an equilibrium mixture. It's already at equilibrium. So I got 3.42. I did 0.16 squared divided by the quantity, 0.24 squared times 0.13. Now, another question you might see is what would be favored at equilibrium? At equilibrium, what would be favored? So I'm just going to make a note here, just kind of a quick thing. Can you answer the question, what is favored at equilibrium? That's always based on K. You're comparing K to 1. So this is slightly bigger than 1, so what should be favored? Products. Because K, right here's your K expression. If this is greater than 1, that means that your value on the top must be a little bit bigger. Right, so products would be favored at equilibrium. All right, so now part C, we need to think back to gases. All right, in part C, it says in a certain experiment. All right, so in a certain experiment, we don't know if we're at equilibrium. We don't know where we are. There we go. But it says in a certain experiment, the system reaches equilibrium at 1000 Kelvin. Okay, so we know we're at equilibrium at 1000 Kelvin. Then the volume of the reaction vessel is reduced from 2 liters to 1 liter at constant temperature. At the moment that this change is made, what are the new values for the partial pressures of each gas in the reaction mixture? Assume that the system has not yet experienced a shift. All right, so nothing has shifted yet. All we have done is we've gone from 2 liters down to 1 liter. Now, this is actually having us think back to past units, past topics. This is having us think about gases. All right, and more specifically, what happens to pressure. So we've already said if we have, let's say now, we're going from a volume of 2 liters down to a volume of 1 liter. What's going to happen to the number of collisions? There's going to be more. Okay, so decrease the volume, increase the pressure. That's what's happening right now. We're decreasing the volume, so we're going to increase the pressure. More specifically, we can look at how much we increase the pressure. How much do we decrease the volume by? What did we do to the volume? Cut it in half. So we cut the volume in half. Well, if we're going to increase the pressure, we're increasing it by the same factor. So instead of dividing it by 2, we're going to multiply it by 2. So if we cut the volume in half, that actually doubles the pressure. So here's where we're thinking back to gases. We cut the volume in half, we actually double the pressure. So if you look back at part B, all of our partial pressures that were given in part B, we change the volume, we're doubling all of those pressures. So instead of 0.24, 0.13, and 0.16, we're doubling those. So 0.48, 0.26, and 0.32. Because the reaction hasn't shifted yet. It hasn't shifted. This is right away. As soon as you cut the volume, you're doubling the pressure. This is actually why when we cut the volume, we see a shift in a certain direction. Because we're immediately changing the pressure and we have to get back to equilibrium. So for part D, use the partial pressures in part C to calculate Q. Okay, so here are the three values. Let's write the QP expression based on KP that we just wrote on the page before. That was the pressure of SO3 squared over the pressure of SO2 squared times the pressure of O2. Remember, Q is calculated the same as K. It's just now we've made a change to equilibrium, so now we're affecting Q. So use these three values, plug in, and solve for Q. So I got 1.71. Now part E. So we calculated Q. We know K. Part E, choose one of the following. So it's talking about which way it's going to shift. It's going to shift from left to right, no shift, or right to left. Now again, look at Q versus K. So what I'm going to do over here to the side is I'm going to look at Q versus K. Q is 1.71. Right, 1.71. K was 3.42. We calculated K in part B. All right, so this is all number 4. So this is all going back. Yeah, so K is 3.42. Q is 1.71. So Q is less than K. Q is less than K. In order to get Q equal to K, we need to increase Q. So this arrow that I drew tells me which way the reaction will shift. I need to go from reactants to products. In order to increase Q, I need to increase the number of products on the top. So if I need to increase the number of products on the top, here's the shift that it's going to make. The arrow points in the shift. It's going from left to right. I'm just going to check mark this first one. Just wants to know which way is it going to shift. Now, part F. Justify the choice you made in part E. Include a comparison of Q versus K. Oh, perfect, because we already did that up here. So here's what I'll say. Always start by saying like how the change that was made affected the system. So I'm going to say since decreasing volume increases pressure of a gas, Q will be less than K. So now I've compared Q to K. Once I've compared Q to K, now I'm going to talk about how that comparison affects the shift. So the reaction will shift to create more products until Q equals K. So the whole point of this shifting is to get Q back equal to K. So if Q is less than K, like this example, we need to increase Q. And to increase Q, we can increase the amount of products. We increase the amount of products, we're increasing our value of Q until it gets back equal to K. This is actually why when we decrease volume, it shifts to the side with, in this case, it'll shift to the side with the least moles of gas. It's actually still Q versus K. Any questions? That was all number 4. I don't see any in there. All right, so now let's look at number 5. Bringing back more old topics, trying to review old topics as we go. So number 5, use the information in the table below to calculate the value of delta H for the forward reaction shown above. Show the setup for your calculations in the space below. I'm going to use just the white equation sheet because when I use the pink equation sheet, the lighting gets weird. So, look here. I see delta HF. Well, if you think back to when we did thermochemistry, we use this equation. Delta H is the sum of the heat of formation of the products minus the sum of the heat of formation of reactants. We're going to use that right now. All right, this one right here, the delta H of the reaction is the sum of the heat of formation of products minus the sum of the heat of formation of reactants. Here they gave us heat of formations. So, I'll write this equation out. Delta H reaction, right? RXN is for the overall reaction. So what we're doing right now is we're calculating delta H. This is going to help us figure out if it's exo or endothermic. So the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. That's from the equation sheet. That equation is from the equation sheet. Now, I'm going to go ahead and fill things in from the balanced equation. So my products, 2SO3. So I'm going to have 2 times the heat of formation of SO3 minus my reactants. 2 times the heat of formation of SO2 plus the heat of formation of O2. And now I can fill in using these values. So, delta H of reaction, 2 times SO3 is negative 395, minus 2 times negative 297, plus 0. They could have not given us oxygen, but remember that the heat of formation of any element in its most stable state is 0. That's why oxygen is 0. Oxygen cannot be formed from its elements because it's already an element. And then I can plug everything in. So 2 times negative 395, just be careful with your negatives. 2 times negative 395, that's negative 790, minus negative 594. So negative 790 minus negative 594, negative 196 kilojoules per mole of reaction. You just did kilojoules, that's okay. The per mole of reaction, it's like mole of RXN. That just means for every one reaction that happens, delta H is negative 196 kilojoules. So, the whole point of this was to figure out what type of process this reaction is. Delta H is negative 196. Is this exo or endothermic? Well, if it's negative, this is an exothermic reaction. Now, will you see questions like this on a quiz or a test? Right now, no. On the AP test, yeah. All right, this is very much like what an AP free response question is like. It pulls in different things. Now, number 6, it was determined that Kp for the forward reaction is equal to 3.42. In another experiment, the reaction is carried out at a temperature of 750 in order to determine the value of Kp. Choose one of the following predictions for the results of this experiment. So notice what we're changing here. Here's Kp at 1,000 Kelvin. Now we're changing temperature. Remember, the only thing that affects temperature, the only thing that affects K is temperature. This is why we needed to know if it was exo or endothermic. Because if it's exothermic, it's inversely related. If it's endothermic, it's directly related. What I told 6th period is it the best way to remember it? Probably not. Endothermic has a D in it, like direct. No, it's a direct relationship. Exothermic is inversely related. So if we look here, temperature is decreasing. We're going from 1,000 Kelvin to 750 Kelvin. And temperature is decreasing of an exothermic reaction. That's important because it's an inverse relationship. So what that means is if temperature is going down, which we know it is, we expect Kp to go up. Do you need to know how? No. Do you need to know the math? No. You just need to know if it's exothermic, it's inversely related. So if temperature is going down, K is going up. So which of these should I check? The first, the second, or the third? We're looking at K is less than 3.42, equal to 3.42, or greater than 3.42. That's at 1,000 Kelvin. If temperature is going down, K should increase. So we should check the third one. And then the very last part, very last pre-lab question, says justify the choice you made in question 6 with an explanation that involves Le Chatelier's principle. Talk about how the change in temperature and whether the reaction is exo or endothermic. So here's what I'll say. When the temperature is decreased, we can think about the change as removing heat. So we're decreasing the temperature, so we think about it as removing heat. Since this is an exothermic reaction, and I'll just say how we know that because delta H is less than 0. The heat acts like a product. So here was the question from this morning. If it's exothermic, is heat always a product? Yes. So since this is exothermic, heat acts like a product. So when heat is removed, the reaction will shift to make more products. Right, so since heat is a product, when we remove it, it's like removing a product. So the reaction is going to shift to create more of what we removed. So increasing products increases K. All right, and if you want to just show a quick, pressure of the products over pressure of reactants. So the reason that we don't use Q versus K here is because when you change temperature, you are changing K. There's no Q versus K here. K is actually changing. So just to show everyone kind of how this website works, this website link is at the top. So if you flip to the next page, I should have put page numbers on here, but if you flip to the next page, it says laboratory experiment at the top. And it has this link. It says go to this link to access the equilibrium system. Or it's linked in Google Classroom. So it might be easier to go into Google Classroom, click on the link that's in this assignment and pull it up. But essentially, here's what this is. And this is exactly what I was going to do in a Google Doc. So another person already did it and saved me time. We have this equilibrium system. So COCl4 2-, which is blue, plus 6 water is at equilibrium with what's called a complex ion. So it's cobalt with 6 waters around it, which is 2+, plus 4Cl- plus heat. So this plus heat is useful, right? Tells us this is exothermic. And then we have this picture. So right now it's purple, which makes sense because one side is blue, one side is red. So if we have amounts of both, it should be purple. Now, in the handout, I showed how to use the simulation. So this Bunsen burner means you're adding heat. This ice bath means you're cooling it down, you're removing heat. Over here, if you add water, KCl or AgNO3. And when you click on it, all it does, right, is it loads a picture. This is all you would have done in lab. And so once it adds the picture, you'll need to just hit the back button to go back to the main screen. There's some important information down here at the bottom in the notes section. It talks about what happens with silver ions. But you can click through, right? You can add heat. Notice it changes color. So here's what it was before. Here's what it was after. You can go the other way. You can remove heat. Here's what it was before. Here's what it was after. And so what I'm going to have you guys do is you're just going to work through the laboratory experiment part. So you have this period, and then you'll have tomorrow as well. My goal is that we get through some of the post-lab questions tomorrow. If I just need to make a helpful video for post-lab questions, I will. But I want to give you guys time to work through this as well. So you'll notice that it's not all clicking and writing. There's also, like, number 1, write the equilibrium constant expression. So write Kc. Then you're looking at the colors. Then you're making changes and talking about which way it must shift. So work through this, right? Answer questions. The laboratory experiment portion goes until number 12.